In Chapter 9, we will be talking about the chain rule and how it applies to implicit differentiation and related rates. So thinking about what we call implicit differentiation, first of all, let's just think about the words explicit versus implicit. What do they mean in English? This is another one of these cases where mathematically words mean very similar things as they do in the actual language that they were taking from. Explicit means that something is given to me directly, whereas implicit means that the thing that I'm after is described somehow indirectly. And this applies to how we've been seeing functions so far. So far, we've been dealing with functions given directly or explicitly in terms of one variable. So we've always seen y equals blah, where that thing on the right had x's only. So all of our functions were given to us directly as y equals a function of x. But that needn't be the case. So for example, let's take a look at this expression. X squared, or a relationship, x squared plus y squared equals 4. That's not given in the form of y equals a function of x. Here we have y's and x's intermittently on one side or both sides of the equation. So if I had to take a derivative of an explicitly defined function, we already know how to do that. I'm going to take a derivative on the left-hand side, which is just y prime, and on the right-hand side, I'm going to apply whatever differentiation rules are suitable. Product rule, sum rule, whatever. But I have no idea how to take a derivative of something like this. So this is what we will call implicit differentiation, taking the derivative of a relationship like this without knowing the exact expression for y. We can always try to take the problem and reduce it to the previous one. So if we can solve this for y, then we have y given to us directly, and we can apply all the rules that we already have learned about. And then we're going to learn this new technique where we will be able to skip that solving step. So let's try both methods side by side to see how they compare. In the first method, I have to solve for y and then differentiate. Fantastic. So let me start with isolating y. So y squared is 4 minus x squared. And now I need to take square roots of both sides, which will of course result in the plus minus. So y is equal to plus or minus square root 4 minus x squared. So that means if I have to take a derivative of it, I actually do have to consider each case separately. This is really not terribly surprising, because if you think of what is the graph of x squared plus y squared equals 4? Well, the graph of that is actually just a circle. Now, and that is exactly what the problem is. A circle is not a function because it does not pass the vertical line test. So what these two cases correspond to are the top circle, where the y-coordinate is positive, and the bottom circle, where the y-coordinate is negative. Top circle and bottom, semicircle and bottom semicircle by themselves are functions, but they're not a function together. So now, in order for me to take a derivative, I'm going to have to take it one sort of branch at a time. But let me rewrite this as a power so I can clearly see what derivative rules to apply. So square root is a power of 1/2. So if I were to now take a derivative of this guy, the outside function is the power. So 1/2 comes down, 4 minus x squared. I subtract 1 from the power, I get negative 1/2, times the derivative of the inside. So this is where the chain rule comes into play. And the derivative of the inside here is minus 2x. Great. So this is just the derivative of the top half of the circle. I still have to do the exact same thing for the bottom half of the circle to produce the derivative there. And this is generally going to be the issue with solving method, is sometimes I will get an expression for the derivative. There's going to be more than one expression for the derivative as the answer. Okay, let's try to think about how would I be able to differentiate that right away. So I'm going to use the dy by dx notation here. We're going to use the prime notation in the next example just to see how that works. But let's start with, I'm just going to take my equation and differentiate it with respect to x. The key here is to remember that this y is actually this thing. So this y has things inside of it. This y right here is itself an onion with layers. So when I'm taking a derivative of it with respect to x, I have to be mindful of the fact that it has an inside. So it is this term that I'm going to have to apply the chain rule to. Okay, let's do it term by term though. So the derivative of x squared is just 2x. There is nothing to it. But we're going to have to apply the chain rule to this y squared. Once again, the outside function is 2, so that's fairly straightforward. The power comes down, gets reduced by 2, but the inside here, y, also has x's in it. Again, like if you solve for it, then you know what they are, but I don't want to have to solve for it. All I have to know is that there is something on the inside, which means I have to apply the chain rule, and the chain rule tells me that once I've taken the derivative of the outside, I have to follow up with the derivative of the inside. The inside here is just y, so the derivative of it is dy by dx. I don't know what it is explicitly, but I don't have to. That's why it's called implicit differentiation. I'm going to take that box and pass it on through the derivative. On the right-hand side, I have 4. A derivative of a constant is just 0, so I have 0. Well, this is actually pretty great news. I've taken the derivative, and what I'm actually after is dy by dx, which is one of the things here, so I can just solve for it. I can isolate it on the left-hand side here, minus 2x, and then I can divide everything through by 2y, so I'm going to get dy by dx is equal, 2's will cancel, minus x over y. Great, and I'm done. This is the derivative of y. So let's compare the two methods. This one is a lot cleaner in the sense that I didn't have to solve for anything. I didn't have to introduce any ugly square roots, and I also really did not have to introduce this split into more than one case. On the left-hand side here, that caused me to end up with 2 different versions of an answer depending on which branch I'm in, whereas on the right-hand side, I have one compact answer. The only downfall to this method, though, is the fact that here, my answer, my derivative, has also both x's and y mixed into it, right? So whereas here, if I start with y equals function of x, then I end up with the derivative being the function of x. Here, I have x's and y's all over the place. Let's take a look at another example and use the implicit differentiation method, but with the primed notation, just to see how that works there. Slope of the tangent line, of course, is a derivative. So this question is just asking to compute the derivative of this function at this point. Great. So let's take a look at this function here. X cubed y cubed minus 3y to the 4th equals 3. Clearly, y and x are all mixed in together. This function is given to us not directly. And there is a problem in that if I could, at least in the previous example, I at least had a choice of methods because I could solve my given equation for y. Here, I don't even have that luxury because the y appears in more than one place. It will be very difficult to solve for it directly. So it's just not even worth the hassle. I'm going to apply implicit differentiation and take a derivative of that as is. And I'm going to use the prime notation this time, keeping in mind that prime means I'm taking a derivative with respect to x. So every time I encounter y, the derivative of y will have to be followed by y prime because y is itself an inside function. So how we're going to take a derivative of this first term here? So the first thing to notice is that before anything else, this is a product. So I'm going to apply the product rule here. So be mindful of the fact that all of the differentiation rules that we already have still apply to these cases. If you have yourself a quotient, you'll have to apply the quotient rule and so on. So the product rule states that I take a derivative of the first thing. Let me actually write this out without proceeding with derivatives first. Plus, I leave the first thing alone, take a derivative of the second thing. So this is what my product rule would tell me. Minus, and then I have to proceed through here. So this minus 3 is just a constant. I can leave it alone and then take a derivative of y to the fourth. And the 3 on the right-hand side just turns into 0. Okay, and now let me actually go through and take those derivatives. X cubed, the derivative of x cubed with respect to x is just 3x squared, so nothing to it. Here I have x cubed and then the derivative of y cubed. So once again, I have the outside function being the cube and the inside function being the y. The chain rule says to take the derivative of the outside function first, and then follow it up by the derivative of the inside, which in this case is y prime. Okay? So every time you take a derivative of something involving y, like y cubed, you have to follow it up by its own inside derivative. Okay? And similarly here, I'm going to have 3, and then the derivative of the outside function is 4y cubed, followed by the derivative of the inside, which is y prime. Great. So let's go back and read what the question is asking. I would like the slope of the tangent line, so I'm after y prime at this particular point. Notice that y prime occurs in 2 spots, here, y prime here, y prime there. So if I were asked for y prime expression in general, I can just isolate those 2 terms on the left-hand side, solve the entire thing for y prime. But in this case, I'm given one particular point. So there's really not necessarily a need for me to deal with all of these unknowns when I can simply plug in the point and then solve for y prime in what remains. Once you plug all the numbers in, you can solve for y prime. And in this case, it should just be a number because you're given a specific point at which to compute the slope. Given a point, the slope is of course going to be a specific number. Okay, I'm going to leave it to you to actually figure out the rest of the algebra here, or if you want to proceed and solve for y prime in terms of all the x's and in terms of all the y's. Implicit differentiation is particularly useful in word problems that involve several different changing quantities, because implicit differentiation specifically tells us how to deal with things that have established relationship, but one is not necessarily solved in terms of the other. So let's consider the next example. Consider a solid spherical tumor. An MRI measures that the tumor is growing at the rate of 0.005 centimeters per month when its radius is 0.4 centimeters. How fast is the volume of the tumor changing at that point? A lot of times, it's not necessarily the size of the tumor that matters, especially when it's small, but rather how fast it's actually growing. Here, we're going to compare the growth of radius, which is a linear measurement, to the growth of volume, which is a cubic measurement. I am asked for how is the volume changing, whereas I am given how fast the radius grows. So first of all, I'm going to need to establish a relationship between the volume and the radius. I'm also told that the tumor is spherical, so we have a relationship between the volume and the radius of a sphere. Volume is 4/3 pi r cubed for any sphere with radius r. Great. So now what I do have, if I were to sort of write down on the side what is the information that I'm given, the information given to me is the fact that the radius is changing at 0.005 centimeters per month. The radius is changing, I'm given the rate of it, and the units should also suggest that I am actually given the derivative of the radius. The derivative of the radius with respect to time, as per units here, is a positive 0.005. I am also told that this is all happening when the radius is 0.4 centimeters. So this is a particular instance in time that I have this information for. Great, that's what I am given. What I want is how fast the tumor's volume is changing. So what I'm after is the derivative of volume with respect to time. Great. Now I have this expression here. All of the things that I am given and asked for are derivatives with respect to time. So I'm going to take a derivative of this relationship with respect to time, keeping in mind the implicit differentiation fact, and that is that this volume is itself changing with respect to time, and this radius is itself also a function of time. Okay, so taking the derivative one piece at a time, the derivative of volume is just the derivative of volume. That's in fact the thing that I'm after. So in this case, we're kind of lucky that the left-hand side is actually exactly what we want. We won't even have to solve for it. What about the right-hand side here? So 4/3 pi is a constant. I don't need to take a derivative of it according to the constant multiple rule. I can take that and keep it. I just need to take a derivative of r cubed. So r cubed, the outside function is the cube. So I take the derivative of outside function first, 3r squared. But then, of course, I remember that r is also a function of time because it's changing with time. So now I need to follow up with the derivative of r. And derivative of r is just dr by dt. Okay, once I have that, again, I can see what it is that I want. I want dv by dt, so I actually want this left-hand side as is. And here, I just need to plug in all the known values into the right-hand side of my equation. So I need to plug in all this given information into here, and I'm going to have myself an actual answer. So we're going to plug in r equals 0.4, and dr by dt was 0.005. Okay, so all together as the answer, once we've computed it all, and you can plug in pi equals 3.14 or some kind of approximation of it, this should work out to be 0.03 units per month. What are the units? Let's take a look at here. It's the units of volume, and volume was radius something times radius cubed. So the units of the volume are going to be centimeters cubed, and the units of time were per month. So when the radius is growing at this rate and it's measuring 0.4 centimeters, my volume is changing at 0.03 centimeters per month.